So the scientific question we're trying to answer is, why do some supercell thunderstorms produce no tornado, whereas other supercell thunderstorms produce maybe a brief tornado, and then a very small fraction of other supercells produce these damaging, long track, wide, devastating, destroy everything in its path tornadoes?
Tracking path will be towards El Reno.
With modern supercomputing hardware and the hardware that's coming down in the future, we are finally able to faithfully represent what actually goes on inside of the most devastating storms known to man. The only way for me to understand this supercell thunderstorm is, first of all, to make it appear like something I'd see if it was coming right for us. If you actually look on YouTube and look up supercell, you'll see thousands and thousands of videos of people chasing storms. And you'll see a dark menacing cloud. You'll see rain falling down. You might see a tornado dancing and causing debris to fly in the air. In my simulation, that's a bunch of ones and zeros sitting on a hard drive now, I can use tools to bring that data to life so it represents those ones and zeros in a way that I can understand. And when I did that, I saw features that looked just like real supercells. So what I do is I use what's called a computer model that is specifically designed to take the laws of physics and to predict what is going to happen next. The supercell thunderstorm is growing and the model is running on the supercomputer. Periodically, it saves data to the hard drive. After the simulation is done, we can look at the data and visualize it. And those pictures aren't being made up. They're taking those ones and zeros and saying, okay, ones and zeros, what are you telling us? What we're seeing in the field using our remote sensing techniques, which is like weather radar, scanning the storm, looking at how much precipitation's over here, what the winds are doing, and I'll go, okay, how does that compare to my simulation? We have all sorts of features that when visualized look very similar to what you see when storm chasers go out with their video cameras. In this case, we started with, if you think of a weather balloon being launched into the atmosphere. So a weather balloon has a little package on it called a radiosonde, and it measures the temperature and the pressure and the winds and the humidity, and it goes up into the atmosphere, and that serves as the conditions for the model to start with. And then we grow a cloud in that atmosphere. Now, we have taken an atmospheric conditions that were actually adjacent to a real storm that produced an EF5 tornado. So this is the May 24th, 2011 El Reno, Oklahoma supercell. This was a long track EF5. So long track means it's on the ground for like, say 100 kilometers, and EF5 is the strongest category of tornado with strongest winds. That is what our simulation produced. Now, we did load the dice, so to speak, in that we chose an atmosphere that was known to produce a real storm. Sometimes we use what are called analytical environments, a very highly generalized atmospheric set of conditions just to sort of get an idea for what's going on. But we use an actual weather balloon launch type input that was right next to a storm that produced a long track EF5. So we're not claiming to have simulated that storm, but we simulated a storm in that environment that looks pretty similar. So we have pretty high confidence that our results are good. We get the cloud going by just pushing the air upwards. It's called a nudging technique. So we go blow the air upwards, essentially. That starts the air moving, and then a cloud will form because of the way the atmosphere works. When you lift moist air, it condenses to form a cloud. When the cloud starts to form, it releases heat, and that heat causes the cloud to get warmer, and then it grows like a big bubble up in the sky. So the cloud starts at time equals 0, and we stop the model 3 hours later. One of the pieces of a supercell thunderstorm is called the mesocyclone, and that's just a fancy word for rotating updraft. So an updraft is air that rises, and in a supercell it's rising because it's warm, it's buoyant. Like if you threw a beach ball in a swimming pool, it would be buoyant, it would float on top of the water. This is a classic characteristic of a supercell. You have a buoyant updraft, but it's rotating. So I was looking at the updraft of the storm and also where the downdrafts are. So with supercells, we have sort of a planned view of a supercell, or a model of a supercell that has the different component parts, such as the updraft. There's 2 regions of downdrafts. There's a front where the cold air from the storm intersects the atmosphere. So all these things that we see in the atmosphere, and we've measured them, and we can see them in models. So for the picture I took, I thought, wouldn't it be neat if you could look at the storm from the ground as if you were lying on your back, looking it up. I saw a lot of the different component features of the storm. I saw the tornado rotating. I saw the downdraft portion of the storm very clearly because I can see it. It's basically hitting the ground, you know, and I'm watching it hit the ground from below. And it just basically brought into focus all the larger scale features that sort of drive the whole supercell during the portion when the tornado is forming. So that's my workflow. You start with a base state atmosphere, you grow the cloud, you perturb the air, get the cloud going, and then let the laws of physics in the computer take over. You don't touch it. It just goes and goes and goes, and that's the simulation part. So once it goes, it just goes, and you just laws of physics, laws of physics, laws of physics. Sometimes the laws of physics don't produce a tornado. That's okay. Sometimes the atmosphere doesn't produce a tornado. If I can get people who might actually be impacted by these types of storms to understand them a little bit better and actually get people thinking about tornadoes and supercells in a way that they might not have thought about before, maybe, just maybe, the next time the tornado sirens go off, people will go, hey, I'm going to go to my basement right now. I'm not going to go outside and look and see that, because these storms are really, really, really violent. So we're just trying to understand this so we can better predict them, so we can get people out of harm's way.